Okay, so we are going to start problem number 4. Okay, so this is just hold on. So this is problem number 4 that we are going to discuss. And what does problem number 4 exactly say? It says that a rod of length L and mass capital M is kept vertically and its bottom end is fixed. Okay, so this is a rod of length L. Let me just draw the diagram. This is a particular rod of length L, and it's this particular end is fixed, and this has a length of particular L, and it has a certain mass M, capital M, and initially it is kept in this vertical position with its bottom end fixed, and the rod is free to rotate in the vertical plane. So let us consider this plane as, for say example, let this be y and let this be x. So it is free to rotate in the yx plane. The acceleration due to gravity is basically in this direction, which is g vector is equals to g of minus of y cap direction, and the rod is given an initial push at a certain time t equals to 0, and it falls freely in the vertical plane, and it falls basically due to gravity, nothing else. So the first part of the question asks you to find the magnitude of the angular velocity of the rod as a function of the angle from the vertical. So as it falls down at a certain angle theta as measured from the vertical, let this be this is the particular angle theta. So you're asked to find the angular velocity of the rod. Now first of all, the rod is a rigid body, so basically all the points on the rod move with the same angular velocity. So first of all, the first thing is that you have to note in order to solve this problem is that the force field, that is the force of gravity, is basically a conservative force, right? It's the gravitational field is conservative. Secondly, gravity is one external force that has been acting on the rod as it falls down. The other external force that acts on the rod is the normal reaction provided by this hinge on the rod, which is along this direction, which is the normal vector provided by the hinge on the rod. Now let us quantify what is the displacement of the rod of this particular end, or let us quantify any particular displacement of the rod which is at a certain distance, say r, radial distance, such as any point P on the rod, which is a certain distance r from the hinge. Its displacement dr vector is basically, since it is rigid, is basically equals to r times d theta phi cap, and the normal reaction is something that points along the radial direction. So the normal reaction is basically the magnitude of the normal reaction times r cap. So basically n vector dot of dr vector is basically equals to 0. So the external work, or the work done by this external normal reaction on the rod, is basically equals to 0. So under this conservative force of gravity, the rod basically falls down, and you can see that the work done by this external normal reaction is 0. So the principle of conservation of energy works. Now how do you apply the principle of conservation of energy? Number one, the rod is rigid and it is uniformly distributed, that the mass M is capital M is uniformly distributed over the rod. So if you calculate the moment of inertia of the rod about this particular hinge O, what you will get is that, and it's a simple exercise to just calculate the moment of inertia of the rod fixed about the particular end O. The moment of inertia is given by 1/3 of ml square. Good. So the center of mass position, since the mass is uniformly distributed, is located at a distance of L/2 from this, from the hinge. So let me just redraw the figure. This was the rod, and this is the certain position at an angle theta over which it is there. Let me draw a circle about the center I mean, it might not be a very good circle, okay, but still it does work out. So this is the position of the center of mass. So this is the position of the center of mass. This is also the position of the center of mass, and this is the fixed end O. So you have to calculate. So for this configuration that is falling down under the action of gravity, what is actually the change of the potential energy? In order to find the change of the potential energy, I mean, even though it is not necessary, but let us fix the reference frame to be this, that is that the potential energy of the system is calculated with respect to this reference frame. But in fact, the change in the potential energy is in fact independent of the reference frame. You could have chosen the reference frame to be this as well, and yet would have you would have got the same delta U. But let us fix the reference frame in this, and let us calculate the change of the potential energy. So this is equals to U2 minus of U1, where basically this particular distance is given by L by 2 of 1 minus of cos theta, right? No, sorry, this is actually wrong. This distance is actually L by 2 cos theta, and this particular length, I mean starting from O to this point P, is given by L by 2. So your U2 is equals to mg L by 2 cos theta minus of mg L by 2, which is equals to m minus of mg L by 2 of 1 minus of cos theta. Okay. So this is your change in the potential energy. Initially, the rod is at rest at time t equals to 0, and after that it has been given a push, it gains kinetic energy. And what is the change in the kinetic energy? The change in the kinetic energy is half of I omega square, where I is basically given by 1 by 3 ml square. Now, according to the work energy theorem as applied to the center of mass, you can have that delta U plus of delta K is equals to 0, as the rod is basically falling under the conservative force field of gravity. And from this, what you get is minus of mg L by 2 of 1 minus of cos theta plus of half of I omega square is equals to 0, where I is given by this particular formula. So if you solve for this, what you can find is that omega, which is equals to theta dot, that is the time derivative of the angular coordinate. If you solve for this, put in the value of I, what you will get it is root over of capital of mgl by the moment of inertia into 1 minus of cos theta. So this is your angular velocity as a function of theta. This solves for you the first part of the problem. Okay. The second part of the problem asks you to find the velocity component of the free end of the rod in the horizontal plane as a function of theta. Okay, so this is part B, and it asks you to find the velocity component of the free end of the rod, in the horizontal plane. Okay, so the free end of the rod is basically, again, I mean, you can think about it, and basically if you compute r dot vector in the polar coordinates, what you get is r dot of r cap plus of r of theta dot theta cap. Even though your choice of the angle is opposite to the normal anti-clockwise convention that you basically choose, even then the formula does not actually change in that sense, and you can easily work it out. It does not actually depend upon the the choice of the convention that you have chosen. But even then, when the direction of theta is chosen in the clockwise sense rather than the anti-clockwise sense, this would still give you the velocity component. Now, for the free end of the rod, you can convince that since the free end is not actually getting off from the surface, or it does not have any radial velocity, for the free end r dot is equals to 0. So you have excuse me. So for the velocity of the free end, that is, for the free end is given by the length L. So it is given by r of theta dot theta cap at the point of r equals to L. So this is L theta dot theta cap, and you're excuse me, and you're asked to find out the horizontal component of this velocity. So as you can notice, since your theta is taken in the clockwise sense, so this is your theta cap direction as opposed to this particular direction, which would have been the case if you had taken theta to be measured in the anti-clockwise sense. So this is your theta, and your component in the theta direction of the velocity of the free end of the rod is equals to L theta dot. So you can basically decompose them. So if this is theta, what you can basically find is that this component is equals to L theta dot cos theta, and this particular component is equals to L theta dot sin theta. So the horizontal component of the velocity of the free end L is given by L theta dot cos theta, where you have evaluated the value of theta dot in the previous part of the question. So this gives you the answer for the part B, that this exactly is the horizontal component of the velocity of the free end. And the third part of the question, the third part asks you at what particular acceleration, at what particular angle the acceleration of the free end of the rod is vertical. So again, let me just list down the acceleration in the polar coordinates, and again, even though you are choosing the angle theta in the clockwise sense, the explicit expression for the acceleration does not change, as you would have got if you had chosen the the convention for the angle in the anti-clockwise sense. And let me just list down the explicit expression. The explicit expression goes like this in the polar coordinates. Excuse me. Okay, so this is your expression. Again, for the free end of the rod is what you have to consider. So for the free end, r double dot goes to 0, r dot goes to 0. So that for the free end r equals to L, you have the acceleration at r equals to L is given by r double dot at r equals to L, given by minus of r, which assumes the value of L theta dot square r cap plus of L theta double dot of theta cap. Again, the same way, you have to decompose them into the the Cartesian coordinates, and mind the fact that your convention of theta is in the clockwise direction. If you decompose that, what you will find is that the acceleration of the free end of the rod is equals to minus of L theta dot square sine theta of, not minus but plus of this particular quantity, plus of L theta dot square cos theta minus of y cap plus of L theta double dot cos theta of x cap plus of L theta double dot of sin theta minus of y cap. So you have to solve for that particular angle in which the horizontal part of the acceleration is equals to 0. So the horizontal component is this and this. So you have to set for that particular angle theta is equals to theta value at which L theta dot square sine theta minus of this plus of L theta double dot cos theta at the value of theta is equals to theta value is equals to 0. In order to solve this, you need to know the value of theta double dot. Even though you have calculated theta dot, you need to know what theta double dot is. And it's quite simple to find theta double dot. Your theta dot square, as was evaluated in the first part of the question, theta double dot square is given by mgl by 2 of 1 minus of cos theta. So you just differentiate it again. What you get is twice of theta double dot is equals to mgl by moment of inertia. This should be the moment of inertia sine theta dot, and if you solve for it, what you get is that theta double dot is equals to mgl divided by twice of I sine theta. So if you put the expression of theta double dot into this expression, what you get as a final answer is as a condition for the horizontal acceleration to be 0 is that what you get is minus of mgl square divided by the moment of inertia times 1 minus of cos theta sin theta. These are again simple trivial algebra that you need to fill in. This is equals to twice of I sin theta cos theta is equals to 0. This is the condition for the component of the acceleration in the horizontal plane to vanish. And if you put in the value of the moment of inertia, the final condition that you get is minus of twice of 1 minus of cos theta sin theta plus of sin theta cos theta is equals to 0. So you have to solve for this equation, and it's quite evident that you can take sin theta to be common, and basically the solution, if you go ahead for this, the solution will be sin theta is equals to 0, or cos theta is equals to 2 by 3. Again, you have to just solve for this thing. It's pretty simple, and I'm pretty sure that you guys will be able to get to this part, that the values of sin theta is either 0 or cos theta is equals to 2 by 3. So what are the roots of this equation? What are the solutions? The solutions are basically theta is equals to 0, pi. The general solution to this equation, sin theta is equals to 0, is that theta is equals to n pi, where n belongs to the set of integers. But since you're basically considering the domain or the range of theta to be 0, less than, theta less than, it should be less than, not less than, equals to less than 2 pi, since again theta is equals to 2 pi corresponds to the same point. So your principal solutions are going to be theta equals to 0 and theta is equals to pi. And the solution of this branch is equals to theta is equals to cos inverse 2 by 3. So what you have are two solutions, in fact three solutions, at which three values of the angle where your acceleration is going to be entirely vertical. Now let us interpret these answers. Obviously you expected that at theta is equals to 0 the acceleration would have been vertical, because at theta is equals to 0 the rod was standing vertically with no angular velocity or angular acceleration to it, and the only acceleration was the acceleration due to gravity. So you expected at theta equals to 0 the acceleration would be vertical. Now are the rest of the answers intuitive? Okay, let us consider theta is equals to pi, right? If we consider theta equals to pi, let us calculate, for example, theta double dot. At theta equals to pi, your theta double dot, what you had got, if you remember the expression, is equals to mgl by twice of I sin theta, and you are evaluating theta dot at theta equals to pi. This is theta is equals to pi. Now sin pi assumes the value of 0, and you get theta double dot at theta equals to pi is equals to 0. Excuse me. If you remember the acceleration was given by the acceleration of the free end r equals to L was given by minus of L theta dot square r cap plus of L theta double dot of theta cap. Now the acceleration of the free end r is equals to L at theta is equals to pi is equals to minus of theta dot square at theta equals to pi plus of L theta double dot at theta equals to pi of theta cap. But you have just now seen that theta double dot at theta equals to pi is 0. So this part cancels out. So there is no transverse acceleration at the point theta equals to pi, at the position at the particular angle theta is equals to pi. So there is no transverse acceleration, and there is only this radial acceleration component. I forgot to wrote this r cap. So at theta is equals to pi, the acceleration is entirely along the center, along the radial direction. At theta equals to pi, the radial direction is obviously along the vertical direction. So you can very well see that again it is quite expected that at theta equals to pi the acceleration is vertical, because there is no transverse component. The transverse component of the acceleration at the value theta equals to pi is 0, and the only component is radial, which at theta is equals to 0 is vertical. The only non-intuitive answer is that you get the answer theta is equals to cos inverse of 2 by 3, At this point also, what you get is that the vertical acceleration is non-zero and the horizontal component of the acceleration turns out to be 0. So this concludes question number 4. If you have any comments, please put it in the comment box, and thank you.